Hello everyone, so today we're going to go over section 8.2 part B, sum, difference, and double angle identities. So we have some new identities here, and notice that in each one we have 2 theta, hence the name double angle identities. So just as an example, we are going to expand sine 2x using the sum identity to show that this first identity here is actually true. So we have sine A plus B is equal to sine A cosine B plus sine B and then cosine A. Again, that is the sum identity for sine. Now what we'll do is let both A and B equal to x. So suddenly, our expression becomes sine x plus x, which of course is equal to sine 2x, and that will be equal to sine x cosine x plus sine x cosine x. And the idea here is that once we have sine x cosine x twice, that is simply going to be 2 sine x cosine x. Right, so that's how we can show that this identity for sine actually works. So the idea for today is to apply these identities to simplify some, or in some cases expand trigonometric expressions. So for example, here we have 2 sine 2 theta. We know that this is equal to 2, and then instead of sine 2 theta, we can have 2 sine theta cosine theta. And so this will be 2 times 2 is 4, so equivalent to 4 sine theta cosine theta. Okay, after that we have on the right hand side here 5 cosine 2 theta. Now if we were to look at the table from above, notice that the cosine 2 theta identity, there's 3 different things it could be. So there's no telling which one we're supposed to use in questions such as these. However, as we move into trigonometric proofs, there are some that will work better than others in some situations. So in this example that we have, we can simply choose any of the 3. So instead of cosine 2 theta here, for example, we can rewrite it as cosine square theta minus sine square theta. And of course, we can multiply this out. So we have 5 cosine square theta minus 5 sine square theta. So that's one possibility. We could also have used the second variation here. So we can have 5 times and then 2 cosine square theta minus 1. So that's also possible. So of course, we'll then have 10 cosine square theta minus 5. And finally, the last possibility we have is 5 times and then 1 minus 2 sine square theta. And that will give us 5 minus 10 sine square theta. So those are the 3 possible expansions using the double angle identity for cosine. Okay, so the next part is the reverse. We're going to simplify some expression that using double angle identities. It's a little bit trickier because sometimes the double angle identities are not as obvious. So then in this first example, we can rewrite instead of 30, we know 30 is 15 times 2. So we can rewrite the expression as 15 times 2 sine A cosine A. And we know that this part here is equal to sine 2A So the expression can be simplified to just 15 and then sine 2a. In the second example here, now in this case, we have to do maybe some substitution here. We will let x equals to 4b for just a moment. So this expression becomes cosine square x minus sine square x. And then we can use the double angle identity. This simply becomes cosine 2x. And now we can substitute the 4b back into the expression. So we have cosine 2 times 4b. And so we'll get cosine 8b. Let's look at this third one here. It's a combination of the previous two techniques that we have described. So the first thing here is to factor out the 3. So we can have 3 and then 1 minus 2 sine square and then 4c. A common mistake here is now let's say we factored by 2 instead of 3. That sometimes we factor out this part as well, but that's not correct. So we're supposed to leave it as sine square 4c. So even if there's a common factor of 2 or 4, that 4c stays together in the argument of the sine ratio. So we can now let x equals to 4c. So we'll have instead 3 times and then 1 minus 2 sine square x. Of course, that means we can use the cosine double angle identity to rewrite this as 3 and then cosine 2x. And then we can substitute 4c back into the expression. So we have 3 cosine 2 times 4c, which of course is 3 and then cosine 8c. Okay, finally, the last one on this page here. This one, again, similar kind of idea. Two things. Number one, we're going to let x equal to 0.5d. And we'll also rewrite 10 as 5 times 2. So there's two different things going on here. So 10 is equal to 5 times 2. And then we can write this as sine x cosine x by letting x equals to 0.5d. So once we've done that, then we have the sine double angle identity. So this will be 5 times sine 2x, of course. And then what will happen is we can back substitute 0.5d back for x. So this will be 2 times 0.5d here inside of the sine ratio. Sorry about that. And so we have 2 times 0.5, which means that the expression actually simplifies to just 5 sine d. And that's it. So let's move on to the next page, where we have some other types of example that involves the double angle identities. So this next example says, if cosine theta is equal to 7 over 25 and theta is in quadrant 4, determine the exact value of sine 2 theta. So we know in this case that sine 2 theta is equal to 2 sine theta cosine theta. And we already know what cosine theta is. It's 7 over 25. What we don't know is what is sine theta. So we are going to need to find that out. So here is sine theta, and we don't know what that is. So we're going to use the diagram on the right here. We know that the angle is in quadrant 4. So go ahead and draw that in quadrant 4. Okay, so we know that the radius is going to be, or the hypotenuse is 25, and that the x value is 7. So we have this triangle here. This is 25, and this is our right triangle. This value is 7. So once again, we have the 25, 7, and 24 triangle. So this side is going to be negative 24. Again, 25 square is 625, and then 7 square is 49. The difference is 576, which gives us a square root of 24. And because it's in quadrant 4, y values will be negative, so this is negative 24. And the conclusion that we get from all this is that sine theta is equal to negative 24 over 25. Okay, so from here we can substitute these two ratios into our identity part here. So sine theta, of course, is equal to negative 24 over 25. And then the cosine ratio is 7 over 25. And so what we'll get is 2 times 24 times 7, and then that will be negative. So that's negative 336 is our numerator, and the denominator will just be 25 squared, which is 625. So that will be the value of sine 2 theta for this question. So one of the goals of this chapter, this unit, is to complete trigonometric proofs. And so this is the next couple of examples will be more like that kind of question. So let's look at this one here. It says state the non-permissible values, then simplify as a single trigonometric expression. So we have here a denominator. And that's the important part because we're looking for the non-permissible value. So we have cosine 2x plus 1 cannot be 0. That means cosine 2x cannot be, of course, negative 1. And then that means 2x cannot be equal to the arc cosine of negative 1. So 2x cannot be equal to, and where is cosine, which is of course the x value equal to negative 1? Well, that will be pi, 3 pi, 5 pi, and so forth. The odd multiples of pi. So if we were to solve for x, we divide both sides by 2. So x cannot be equal to, so what we want to do first, sorry about this, is to generalize the result. So we have 2x cannot be equal to pi plus 2 pi n. So that is all the odd multiples of pi, both positive and negative, of course. And so finally, we divide both sides by 2. So x cannot be equal to pi over 2 plus pi n, where n is an integer. So that is our non-permissible value. It's a little bit more complicated than usual. If we were to use a double angle identity for cosine 2x, it may have been simpler, but nonetheless, we do have this result. X cannot be pi over 2 plus pi n, where n is an integer. So that's the first part. The second part is to simplify the expression. So in this case, we are going to use the double angle identity for both sine and cosine to expand the expression. And so in the numerator, we're going to have 2 sine x cosine x. And then in the denominator, we are going to have, let's see here. So it says cosine 2x plus 1. And we know that the double angle identity for cosine, there are 3 different possibilities. And the one that we're going to choose is going to be the one that has a negative 1 in it, because that will eliminate the plus 1 in the expression. So we're going to go ahead and rewrite cosine 2x as 2 cosine square x minus 1. And then this plus 1 comes from the original expression. So once we combine the like terms in the denominator, we are going to get just 2 sine x cosine x in the numerator. And the denominator is going to be just 2 cosine square x. And of course, we have some factor, so it will be eliminated here. For example, the 2's will be gone, and also one factor of the cosine x will be gone. And so this whole thing simplified to just sine x over cosine x, which we know is just tangent x. So this particular expression actually simplifies quite nicely to just being tangent x. Okay. So from here we can move on to the next piece. Again, state the non-permissible values, and then we're going to show that the expression is equal to 1/4 cotangent 2x. So let's see what we can do with this one. And again, we want to start with the non-permissible values. So on the left-hand side here, in this case, we know that sine x cannot be equal to 0 because it is in the denominator, and also cosine x cannot be equal to 0, same reason. And so in this case, we can use the combined restriction. As we have seen before, x cannot be equal to pi over 2n, where n is an integer. And in previous sections in this unit, we already talked about why that works. So from here, the right-hand side, it should be obvious that we can factor out the 3 from both the terms in the numerator. So this will just be 3 and then cosine square x minus sine square x. And then in the denominator, we're going to have to rewrite this as 12 times, and then we can use parentheses here, even like so 2 times sine x cosine x, sorry about that. All right, so the numerator, the cosine square x sine square x, can be rewritten as cosine 2x using the cosine double angle identity. And in the denominator, the 2 sine x cosine x can be rewritten as sine 2x using the sine double angle identity. So the 3 divided by 12 is going to give us 1/4. And of course, cosine 2x divided by sine 2x is going to give us cotangent 2x. So we have the expression that we want. Okay, so lastly, just a couple more examples here. It is to, let's see, write as a single trigonometric. Again, this is not a function, this is an expression. Sorry about that. Okay. And then we can find the exact value. So very similar to the question that we had seen before. Notice here we have 15 degrees, which is not a special triangle value, and neither is 7 pi over 12. So by using our double angle identities, we can rewrite this so we have values that are special triangle values. That's the idea. Now, one very important fact about this first question, part A, is that 1 is equal to -1 plus 2, which is obvious, but it's going to be very handy here. So we can rewrite this expression as 2 cosine square 15 degrees minus 1 plus 2. And the reason why we did that is because 2 cosine square x minus 1 is a double angle identity version of cosine 2x. So we can rewrite this as cosine and then 2 times 15 degrees and then plus 2. And the idea here is that, well, 2 times 15 is just 30, so this is cosine 30 degrees plus 2. And we know that cosine 30 degrees is root 3 over 2, so the whole expression simplifies to just root 3 over 2 plus 2. And again, this question becomes a lot easier if we are able to use the fact that 1 is equal to -1 plus 2. Kind of a trick to doing that question. So for the second part here, we can simply factor out the 2, and then we're going to have 1 minus 2, and then sine square 7 pi over 12. So that's the first step. Second step here, notice that we have the 1 minus 2 sine square and then 7 pi over 12. That is, again, a double angle identity for cosine, so we can rewrite this as 2 times cosine and then 2 times 7 pi over 12, which actually simplified to 2 and then cosine 7 pi over 6. And of course, 7 pi over 6 means that the angle is in quadrant number 3, where cosine is negative. The reference angle is pi over 6, which means that the trig ratio is just going to be negative root 3 over 2. So again, that information should be written down. This is quadrant 3. And then the reference angle is pi over 6. All right, and then from there, we have 2 times root 3 over 2. So that will simplify to just the the negative square root of 3. And that's it. So this last 2 questions kind of tricky just because we have to anticipate what the special triangle angles are going to be that we can find. So for example, we want to find 2 times 15 is 30, so we can use the special triangle in example A. Same thing for example B as well. Pi over 12 is not a special triangle number, but pi over 6 is. So again, just looking for ways to utilize the double angle identities. But that's it for today. So once again, thank you for listening.